Welcome back, everybody. Hope you guys had a good week. Oh, gotta let some more people in here. Okay, excuse me. Well, first I want to thank you for your indulgence in allowing me to change, or having to change the times for the last 2 Fridays. That allowed me to finish up and close in his house. So now the real work is unpacking. So anyway, hope everyone had a good week. Don't forget, tomorrow opens up exam number 2, chapters 4 through 6. Okay, so make sure you give yourself plenty of time to complete it. And if you don't have any questions, I will continue where we left off last week. We ended up on chapter 7, slide 21. So are there any questions you need for me to address? A quick note about all the assignments on Canvas. For some reason, I have graded the labs, but for some reason the grades are not updating. So I'm working that up. So it goes back to lab number 2, which is kind of crazy. Anyway, I hope to have that corrected by the weekend and everything get updated. Second thing, if for any reason you're doing any quiz, homework, whatever through Canvas, and you don't see an image, it's a tech problem with respect to Canvas. Just let me know which assignment it was, and I would, no question, give you credit for that. It is recommended by tech support to use the Chrome browser. But even you doing that, sometimes for who knows why, an image, one person sees the image, the other person doesn't. Okay, so for future reference, if you don't see it, don't get upset about it. We'll give you credit for that. You may have noticed I sent an image to everyone, I think last week, for that particular reason. Okay. Any questions? No? All right then. Well, in that case, I will continue. We were ending up in chapter 7, where we were working out the procedure of creating Lewis dot structures of molecules of compounds. Okay, previous to this, we did the Lewis dot structures of specific atoms, and that was only for the A elements. Okay, and it's basically just putting dots around the symbol depending on how many valence electrons it has. So here now, from that point, we started to put them together with respect to determine the structure of a molecule given. Now, point number 1. You always know who is the central atom. There's always an atom that's in the middle of the whole structure of the compound. And then everything else is bonded to the central atom. The central atom, a lot of times, will be denoted by underscore or even written in bold. Okay. That's point number 1. Point number 2, what we do is we add up all of the valence electrons that each atom brings to the molecule. Okay, when you do that addition, you should have a number that is divisible by 2. If you don't, then maybe you wrote down the wrong valence, the number for the valence electrons. So go back and double check. You're always going to have a number divisible by 2. Once you know the central atom, you can write the central atom down. For example, we did this one here for water. Water, H2O, has 2 hydrogens, and so therefore every hydrogen brings in 1 valence electron, and there's 2 of them, okay? And then the oxygen brings in 6 electrons, and so we have a total of 8 valence electrons, and it's divisible by 2, so that tells me I have 4 pairs, okay? Now I choose to select the pair because it can simply draw a line. A line is a terrible line. A line represents a pair. There are 2 electrons there. And it's much easier and quicker just to draw a line. Now, if you prefer to do the double dots, go for it. They'll make it, you will not be incorrect if you use double dots. So we have 4 pairs to work with. The key point about that is that's what you have to work with. You can't just add or subtract, or for some reason, maybe you end up with extra electrons. You just can't throw them away and say, oh, I don't need them, I don't use them. You have to make the 4 work, assuming obviously that you got this part correct as far as valence electrons. Remember, the valence electrons, the outermost electrons of the atom, that's where all the chemical process occurs. That's where all the bonds are being formed and so forth. The core electrons, the ones inside, they're not involved with anything. You know, they're happy, the inner core, you know, the inner core, they're happy with 8 electrons or 2, depending which one we're looking at. All right, since water, normally this would be underscored, water is a central atom, we can quickly just write O for oxygen. And we know, given the formula, that there are 2 hydrogens, that therefore we can quickly draw a line and hydrogen, and that represents that 2 hydrogens have been bonded to the central atom of oxygen. Well, since we have 4 to begin with, that takes care of 2 bonded electrons right here and right here. So now we got 2 remainder. Now we can't put them on the hydrogen, and because the hydrogen's rule is a duet, okay? This electron pair sitting here is being shared by both the hydrogen and the oxygen. And so they count both toward the hydrogen and toward the oxygen. Okay, so the duet rule for hydrogen doesn't allow us to put any more hydrogens, any more electrons on the hydrogen. Remember that hydrogen only has 1 bond, that's it. So that you might ask, well, where do I put the remaining 2? Well, the only obvious choice would have to be in the central atom. And I can put them, and I draw my lines right there, and now I have 2 lone pair. Remember, these are lone pair because they're not bonded on the oxygen. Now, count the octet / or duet. Duet for hydrogen means 2. Hydrogen's okay with respect to its duet rule. And then we count the number of electrons around the oxygen. Let me draw it over here a little bit better so get away from all that mess there. Now I put the lines, or if you're happy, you can put the 2 dots, either one. And if you count the total number of electrons around the oxygen, you'll find it 8. So the 8 electrons around the oxygen. 2 pair, or 4 of them, 4 of the 8 are lone pair. Okay, and the other pair, or 4 more, the other 4 electrons are bonded. Okay, all right. Once we have come up with the structure, verify that you have 4 pair of electrons all the way around, or 8 electrons, because that is what you calculated here. And you do an inventory, and sure enough, we got 8. We didn't lose any along the way. It is feasible to lose them, and it's also possible to add more mistakenly. So double check, always check at the end. Now with that information now, since you have this, we create the general formula. The general formula is the ABE format, okay? A is always the central atom, and it's 1. A is always by itself, just 1. B represents whatever atoms are bonded to the central atom. They can be the same or they can be different. It just means the total number of atoms bonded to the central atom. And in this case, we have 2 hydrogens, so B has a subscript 2. E represents the number of lone pair of electrons on the central atom. Now, you're going to have examples where there are lone pairs on what is bonded to the central atom. We don't care about those, only what is bonded to the central atom. And what we did here, we identified 2 lone pairs. So in this case, we have an E. You don't always have an E. The subscript represents how many lone pairs you have for both, how many atoms for B2 and E2, we got 2 lone pairs, 2 atoms bonded to central atom. So our general formula that we utilize now, that we need to know, is A, B2, E2. Now, what do we do with that information? Well, once we know that, we go to the shapes table. And if you've not downloaded that shapes table and not familiar with it, that's a good time because you're going to utilize it quite a bit. In the shapes table, to refresh your memory, we have 4 columns. We have the general formula of ABE, and that general formula has with it associated a molecular geometry, which shows you the model of that compound, of that molecule, in a somewhat of a 3-dimensional format. The next column gives you the name of that shape. And then the final column gives you the bond angle between what is bonded to the central atom relative to the items bonded to the central atom. So for example, let's look for the AB2E2, the one we just did. Let me clear this up a little bit. And we have it right there. So this is the central general formula that we determine from the Lewis dot structure. And the Lewis dot structure we determine from counting up the valence electrons and putting them together like we just did. So there's AB2E2. That is the general configuration, the general geometry in a somewhat of a 3-dimensional format. Here we have the central atom, which is oxygen, and then the 2 hydrogens bonded to the oxygen. Then here's the lone pair. Now, that kind of oblong shape, that's just kind of overemphasis trying to show you where the lone pair are sitting, okay? And so it's not like it's got an oblong thing, it's just showing where the lone pairs are sitting. And normally there's a bond angle between the hydrogens of 109.5, and I'll explain here in a minute, but it's not, and I'll explain in a second. That geometry is called bent, and that bond angle is less than 109.5. Now, why 109.5? That is because the reference point of geometry is called AB4. That geometry is pretty standard out here in nature, the structure of compounds out there. And you can see you have the central atom and 4 atoms bonded to the central atom, okay? That has a specific name, it's called tetrahedral. Now, remember that at each line represents 2 electrons. And so we got 2 electrons with a negative charge on each bond. They're going to repel such because they're negative charge. Not only are they repelling with each other, they're going to repel with other electrons in the molecule. So in this configuration, this is where they can get away the position so that there is repulsion throughout all the way around, and it ends up as follows. If these were little springs, for example, and these were like the balls represented maybe like a positive charge or negative charge, they're all going to repel each other and they'll end up in that configuration. That bond angle is 109.5, okay? But what happens is, if I were to take one of these bonded atoms from the central bond away, we end up with lone pairs, okay? Here we got 2 lone pairs right here and right here, I should say, and right here. Well, those lone pairs, again, are negative charge, as we just stated, are electrons. So they're going to repel from each other, and they're going to kind of move away from each other. The result is that these bond angles that we would anticipate to be 109.5, based on our reference point, are much less, because those electrons, lone pairs here and here, take up most space. That bond angle, that bond angle gets squished in, and hence that's why we get less than 109.5. The other aspect about anytime you do an electron configuration and you end up with lone pairs in the central atom, we can automatically say that structure is polar versus nonpolar. What do we mean by that? Well, water, for example, remember, the old adage, like dissolves like. We know that water and oil do not mix, okay? Take a look at Italian dressing. You got 2 layers, an oil layer and a water layer, okay? They will not mix. The water layer is polar. The oil layer is nonpolar, okay? And when we get a lone pairs on the central atom, 9 times out of 10, you end up with a polar molecule. We're gonna learn about that here pretty soon, because we need to know from see how it's all connected. We start off with the atoms in their valence electrons. Now we're starting to put molecules together. We put them together, then we're going to determine whether we've got a polar bond, okay? And then depending on where the polar bond is, we're going to end up with the whole polarity of the molecule. But more on that in a second. So this part here is like an introduction of what's coming in. Okay, so once we have that information, with respect to the the general formula, which again, we are able to determine its geometry, and from that, the bond angle, okay? All right, so now what we do here is same thing, all right? Now, what we do is simply, here they're telling you that carbon is the central atom, okay? But we need to tally up the valence electrons. We know hydrogen brings in 1, carbon brings in 4, and anybody know how many valence electrons nitrogen brings in?
3.
3? What group is nitrogen? Look at the periodic table behind me. Or not, you got
Sorry, 5.
Yeah, you got it. All right. And so nitrogen brings in 5 valence electrons, carbon brought in 4, and hydrogen brought in 1. So we tally this up and we end up with 10, which is divisible by 2, which tells me I have 5 pair of electrons to work with. And that's it. Okay. No more, no less. Okay. Now, carbon is a central atom, so I can put carbon in the middle, and very quickly I can add the bond, the hydrogen and the nitrogen. So I draw a line for the hydrogen and the line for the nitrogen, okay? Because I'm given that right there. Well, that takes care of 2 pair, okay? So now I got 3 pair left to work with. Now, where I put them is, well, first of all, we can't put any more, I hope you can see this. We cannot put any more electrons on hydrogen because that will violate the rule for hydrogen, which is a duet. It has 2 electrons around it being shared with carbon. So we're maxed out on hydrogen. That means I can, the rule for the other atoms is an octet. And so we can apply them anywhere we want for the other atoms. I prefer to put them on the outside atoms and work my way in. So we got 3, so I just quickly write 3 lines, okay? And then I do an inventory check of my pairs, and I got 1, 2, 3, 4, 5. Well, that 3 took care of it. I still have 5 pair to work with, okay? I didn't lose any. All right, now we check to make sure the octet is fulfilled for these atoms. We know, as we just discussed, the hydrogen's happy. Nitrogen is also happy because it's got 8 electrons around it. Okay, so nitrogen checks out. Carbon doesn't check out. Carbon only has 4. Okay, so now what we do is we cannot magically just grab electrons from the air and pull them in and make a bond. We take from a neighboring atom and we create a double bond and or a triple bond until the octet is fulfilled for everyone. And so we're going to very quickly take this pair here and create a double bond between the carbon and the nitrogen. And so we got a double bond here, and those other 2 lines are still there. Okay, here again, every step take an inventory because you can lose things, and we still have 5 pair, which means, okay, we're still good, okay? 5 pair. Now check for the octet. Nitrogen's still good with 8, hydrogen's still good with 8, carbon not so good. It now has 6. So what do? We again make share another pair with carbon. So now we can create a triple bond. And so what you're doing is you are creating with the lone pairs that you have, okay, that's important, with what you have, and you are creating double bonds, and that doesn't work, go up to triple bonds, and that's it, maximum. We're talking about either single, double, or triple bonds. There's no such thing as quadruple or or 5 bonds or anything like that, just triple bond, double bond, or single, okay? Now, doing inventory, we still have 5 pair. 1, 2, 3, 4, 5. We're still good. So now check the octet around the molecule. Hydrogen still good. Nitrogen is still good. It has now 1 lone pair on the nitrogen and then 3 pair being shared with the carbon. So that's a total of 8. So nitrogen is good to go. Carbon now is sharing those same 6 with nitrogen, and then is sharing 2 with hydrogen, so it has 8. So we're good to go, okay? Now, we do the general formula, okay? And carbon is A, and then we got B, which is 2, because hydrogen and nitrogen are bonded to the central atom. We don't have any lone pair on carbon, so there's no E, okay? And so that's our general formula, AB2. We then look up that general formula on the periodic table, on the shapes table. Here's AB2 right there, okay? That's a shape. So here we got carbon in here, nitrogen right there, and hydrogen right there. Its geometry is linear, okay? In fact, anybody with the AB2, or for that matter, if you have something that's just too, like a diatomic, let's say fluorine, diatomic, guess what? It's linear. They got two atoms, whether it be the same or different. You cannot have any other geometry than just linear, okay? And if for 2 atoms, the bond angle really wouldn't be a factor there because there's no bond angle to measure. So you got to have a minimum of 3 items, 3 elements to give you a bond angle here. So for the one we're doing, HCN, it is linear and the bond angle is 180 degrees, okay? So let's go back and let's see. There it is, okay? All right, this one's
I have a question.
Sure, go ahead, go ahead.
So I know it's underlined in this example, but otherwise, how do we know what the central atom is? Like for the next example, it looks like the H would be, but it's not.
No, you see what's underlined? The carbon.
But like if it's not underlined, you know, like if we just have to determine it on our own, how would we know?
I can answer it this way. 99% of the time, it'll be underlined or in bold, and that would tell you. When it's not, you can assume pretty good 99.99% that the first atom that is presented in your formula is a central atom.
Okay.
Okay? All right.
Okay, thank you.
Yeah, good question. Yeah. Underline or the first atom generally would be the central atom. All right, well, let's take a look at the next one. Okay, we have carbon, which as we saw earlier has 4 valence electrons. Hydrogen brings in 1. Fluorine, there's 3 of them, right? And how many does each fluoride bring in? What group is it in? Look at the periodic table behind me if you don't have it.
Brings in 7.
Exactly. And there's 3 of them. So therefore we have a total of, 3 times 7. So we got 21, okay? So we have a total of 26 valence electrons. These valence electrons are the ones that are going to give the shape and the geometry of the molecule. So we got 26 or 13 pair to work with, okay? Now, carbon here is shown to be the central atom. So we got carbon, and then we have a hydrogen bonded. Where you put it makes no difference. And then we got 3 fluorides bonded around the central atom. So we can very quickly place them around the carbon. Okay, so that took care of 4 pair. So now we have 9 paired to work with. Okay. And so we look at this and we say, well, hydrogen is again always one. That's like a cardinal rule. Hydrogen only has one bond. And so we cannot put any more on the hydrogen. Okay. We look at the carbon. Carbon has 4 bonds. Now remember, carbon will can have a combination of 4 bonds like shown, or it can have a combination of a double bond and 2 single bonds, or it can have a combination of a single bond and a triple bond. Okay, but there's no more than 4 pair around it. Here we see we have 4 bonded around carbon. So guess what? Carbon is happy. Okay, its octet is fulfilled. So one should be like, okay, well, where do I put the rest of it? Well, the only place you can put them would be on the fluorides. Okay, because the way it's written here, I only showed 2 electrons on each fluoride, and it needs 8. So obviously that's the only place they can go. I have 9, so I just start and make 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the 4 inside, 10, 11, 12, 13. So I started with 13. I ended up with 13. Okay. So on the general formula, we have A and B will be 4. Okay. We remember B represents anything bonded to the central atom. In this example, we have 1 hydrogen and 3 fluorides. So our general formula for this species is AB4, which, if you recall when we were talking about that one, AB4 is pretty much the standard shape, which is right here, which is tetrahedral, okay? And it has a bond angle of 109.5. All right. Now, this type of information, really from an organic chemist, when we synthesize compounds, really gives us a lot of information about the reactivity of the compound. Because when we sit down and we analyze it, we got to try to make a compound, maybe for medicinal purposes or maybe for any application. We have to look at the molecule and look for certain things in the molecule that actually deal with polarity to see if we can change it. A lot of the antibiotics, the penicillin-based antibiotics, the standard formula, I shouldn't say standard, the base formula is the same. What they've done is they adjusted groups here or there, and to see if it would enhance the properties of antibiotic properties. And sometimes it does, and sometimes it doesn't. Okay, so now that's what we came up with, tetrahedral. All right, this brings us to CO2, carbon tetrachloride. Excuse me, carbon dioxide. Okay, CO2. So we have carbon again, 1 carbon, that brings in 4. The oxygens, there's 2 of them. And what group is oxygen in? How many valence electrons does each one bring?
6.
6, exactly. That means we got 12 total. Okay, don't forget that number. We got 2 oxygens, so we have to account for each oxygen. And so we have a total of 16 valence electrons, or 8 pair. Okay, 8 pair to work with. Carbon again is underlined, and if it wasn't, it would be the first atom there, and therefore that is the central atom. And then the only exception to that is when you have acids. This guy is really an acidic. Well, when you see hydrogen out there, hydrogen will never be a central atom. First of all, it can only bond one bond. So hydrogen put out there wouldn't be the central atom. That means, that's why I say 99.9% of the time, the very first atom written down is the central atom, if it's not underscored or bold. Okay, so now we can put carbon in the center, and then bond 2 oxygens to it. We have 2 of them, and that takes care of two pairs. So we got 6 pairs to work with left over. Now, where you put them makes no difference. You can put them in any combination that you want. I like to put them on the outside and work my way in. So I got 6 to work with. So I go 1, 2, 3, 4, 5, 6, and then I had 7 and 8. So that takes care of the 6 pair. I count to make sure that I still have 8, and I do. So I keep track of that. I still have 6 pair to work with. Now I check for the octet. If you look at the oxygens, both the one on the left and the one on the right, they're happy. Okay. However, carbon only has 4 around it. So just like we did on the first one, we got to take from Peter to share with Paul, so to speak. So we're going to do it both ways. We're going to take a pair from here and make a double bond, and then we're going to take a pair from here and make a double bond. Now you can take 2 pairs, but that's going to pose a bit of a problem. Okay. So when you have a situation like this where you can take pairs, the central atom is shy of electrons, take 1 pair from each atom it's bonded to, and then see how that works out. The result is this: we make carbon double bonded to oxygen, carbon double bonded to oxygen on both sides. Check to make sure we still got 8. When we do, we got 4 bonded pair and 4 lone pair on the oxygen. So we still have 8 pair. We didn't lose anything, nor did we add any more by accident. Okay, now we check the general formula, which would be AB2. And you can look that up on the shapes table. It's going to be just like the first one we did. It will be linear. Okay. More importantly, we're going to learn here in a bit that this geometry for carbon dioxide gives it the property where I mentioned earlier about polar and nonpolar. Because of the geometry, it actually makes it into a nonpolar compound molecule overall, even though it has what we call polar bonds. And more on that in a bit. And this is this part's important, because we're going to take this information, and then when we have the compound and the molecule, then we have to decide additional properties, and that's going to be decided by the geometry of the molecule, which we don't know, we can't offhand unless we figure it out through the Lewis dot structure. Okay. All right. So there we go. All right, so now we do nitrogen and hydrogens. Now, obviously, I haven't given the names, but if you got a kid around the house, you got some dirty diapers, this is what you're smelling. This is the structure for ammonia. Okay, so we have nitrogen that brings in 5 valence electrons, and then the hydrogen brings in 3. There's 3, brings in 1, but there's 3 of them. And so we have a total of 8 valence electrons, or 4 pair to work with. Okay. And so we got nitrogen. We can put it down real quick and then attach to it 3 hydrogens, because that's the formula that we were given. And that takes care of 3 pair, leaving us 1 pair to work with. Well, obviously we cannot put that on the hydrogens. Okay, because again, the hydrogens are duet rule and they're happy. So the only place they can go would be on the nitrogen. And here I'm just going to put 2 dots. Okay, double check. It could be 2 dots or a line, makes no difference. And we do have 4 pair. We haven't lost any. Now we make the general formula, and that would be AB3 for the 3 hydrogens. And guess what? We have a lone pair on the central atom. So we have an E here. So it's AB3E. Okay. With that information, we then go to the shapes table as before, and we look for AB3, and there it is down here. Okay. And here's a general formula. This can represent nitrogen could be in the center, and then the 3 hydrogens around it. And then here's the lone pair right there. And that has a very specific name. It's called Trigonal Pyramid. And its bond angle is much less than 109. Again, why? Because that lone pair takes up more space, because those two electrons are going to repel from each other, forcing the hydrogen, nitrogen, or the bond angle here to get smaller, okay, by force, by the force of those lone pairs. And again, as I mentioned before, we have lone pair on the central atom. Guess what? We have a polar molecule. That'll make more sense here in a bit. All right, let's go back. And there it is. Okay. All right, now this so far has been for, this exercise has been for neutral structures, neutral molecules, okay? Notice there's no charge in them, okay? Now, this is a rehash that we just talked about with respect to the first example, okay? Just going through step one. So again, this is neutral species. Now we're going to talk about Lewis dot structures of what we call polyatomic ions. Okay, well, let me introduce that. You might as well, you're going to become familiar quite a bit with these polyatomic ions. If you look at the periodic table on the bottom left corner, there is another table, and it's listed as most common polyatomic ions. Okay. There are things like, let's look at NH4 plus, okay, that's called ammonia. These are units, okay? These polyatomic ions come together, bonded and together as a unit. Now, because of the nature of the beast of these guys, these ions, they have a charge, either a positive charge or a negative charge. You notice the majority of them are negative charge or anions. And yes, there are some more positive, but the one we're going to use a lot is this one called the ammonium. The thing about this is these guys, these polyatomic ions have a specific name. We don't change the name. We don't say nitrogen oxide, whatever. It's called nitrate, for example, or nitrite, sulfate, sulfite, et cetera, hydroxide, OH, cyanide, CN, etc. Okay. Hydrogen bicarb. This is good old-fashioned baking soda. Here's HCO3 negative. They also have a configuration that we can determine using the same process that we did. The only difference is we're going to add or subtract a number depending on their charge. Okay. We're not adding or subtracting ions. We're accounting for the fact of the charge. So the thing to remember is, well, how do we charge, or do we add or subtract? Well, it depends on the charge of the ion. We do the same steps as before, nothing new. Okay. If it is a negative ion, we're going to add a number to it, depending on, we're not really adding electrons. It's kind of those electrons are there, they were bounded with something else, but that something else was removed and resulting in the charge of that ion. Okay, so we have to account for it because initially they were brought to the center, they were neutral. These ions at one point in time were neutral species. Most of the time, the negative ones, a hydrogen was removed. So that hydrogen brought in an electron. But when it was removed, it went away as positive and they left behind the polyatomic ion as negative. And the same is true for the ammonium positive. At one time it was neutral ammonia, but then a proton came in, a hydrogen plus came in and tied up that lone pair. Remember the lone pair in nitrogen? It tied that up and it gave an overall plus charge. Okay, so we have to account for that. All right, so we add a number, and then the quantity that we add, if it's negative, depends on the charge. So if it's a -1, we just add 1, -2, add 2, etc. If it is positive charge, which we only got really one, actually the ammonium, there are others, we just simply add, subtract 1, okay? Remember, keep in mind that you will always have a number divisible by 2. And if you forget to add or subtract and you end up with an odd number, then something went amok. Go back and check, making sure you're going the right direction. Also, if you reverse this, let's say it was negative and you subtracted, well, you're gonna see that no matter how I move the electrons that you have left over, you're not going to have enough electrons to complete the structure. So, or if it was positive ion and you added, you can have an excess amount, and there's no place I can put that. Those are flags to tell you, let me go back and check my math. All right. The only difference between the neutral compounds in these, that once you come up with a structure, then we put a bracket around it and we put the charge on the upper right corner, and that represents and tells us that it is a ion with a specific charge. Let's take, for example, the ammonium ion. There are 1 nitrogen and 4 hydrogens, and it has a plus charge, okay? And so like we did before, nothing different. We account for the electrons that nitrogen brings in. There are 4 hydrogens here, so we add a 4. Notice if we forgot to do this last step here, we end up with 9, not divisible, okay? Positive charge, then we subtract 1, so we have 8 valence electrons to work with, okay? Nitrogen, notice here, it's not underscored, but like I stated, hydrogen, you will never find hydrogen to be the central atom. So by default, nitrogen is the central atom with 4 pair. So we can very quickly go NH and N, and then bond the 4 hydrogens. And that takes into account those 4 pair, okay? And then we put this bracket over the whole thing, and then we put the charge in the top right corner, okay? Now let's say, for example, you did the 5, the 4, okay? And then you, instead of subtracting, you added, right? So you got 10, and now you got 5 pair, okay? All right, let's go that round. So that's what you did mathematically. So we know that we got nitrogen, and that takes care of 4 of them, like we just did, okay? And that's 4 of them, but you got 1 pair left. Now, we can't put them on hydrogen, and you can't put them on the nitrogen, because the nitrogen's got 4 pair around it already. And so that 1 extra pair tells you, hopefully, that you added rather than subtracted. See what I'm saying? You got an excess number of valence electrons to work with. And so you go back and check your math to make sure you did that correctly. All right. After we're done with this, that's your structure. We can now do like we did before, come up with a general formula, which still ABE. So this case is AB4. And if you go look in the shapes table, that is tetrahedral. So this polyatomic ion has a geometry of tetrahedral with bond angles of 109.5. Okay. It just happens to be an ion and is charged. Okay, so that's our formula right there, what we just went through. All right, now, some of these, you know, what they are right now, not important at this point. We're just going to go through the exercise of figuring out the Lewis dot structure for these polyatomic ions. Procedure is the same. We got bromine that brings in 7 valence electrons. There's 3 oxygens for a total of 18, okay? And then we add a -1 because it has a -1 charge, okay? That gives us a total of 26 valence electrons or 13 pair. All right, so bromine is the central. Notice I said bromine, not bromide. When bromine is the central atom, these are legitimate compounds. The name stays bromine, And only when it's attached to something else as an ion, it's bromide, okay? All right, so we got bromine, and we have 3 oxygens bonded to the central atom. So I can very quickly do this, all right? That takes care of 3, so I got 10 pairs to work with left over. All right, so now put them in where you want. So I'm just start on the outside and work my way in. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that took care of 9 pair. I got 1 pair left to work with. Well, the only obvious place to put it is in the central atom because all of the oxygens are full with 8. The octet has been fulfilled. So the only place I can put them is in the central atom. I just draw a line. Now double check to make sure you got 13 pair. Sure enough, I got 9 around the lone pair around the oxygen, 9, 10, 11, 12, and 13, okay? I draw my bracket around it and my negative charge, and that is my structure. Let me bring the other one in so you can see that. A little bit better drawing than what I did. Okay, general formula, no different than before. We got A, B3, and guess what? We got E. Okay, with this general formula, then you go and look it up and figure out what is the geometry. You'll find it to be very similar to the ammonia that we just did, geometry-wise. All right, next one, we got SO4 -2. This is, by the way, is called sulfate. Next time you're eating something, you'll find, look at the label, you'd be surprised how much sulfates we're eating. And if you like wine, you might be drinking what I call sulfites. Sometimes read the label about sulfites. I don't drink wine because the sulfites, I guess I'm allergic to them. They're constrictors, vasoconstrictors, and give you a headache like that. All right, sulfate, excuse me. We take sulfur brings in 6 valence electrons. Oxygen, there's 4 of them. Each one brings in 6. So we got a total of 24. There's a -2 charge, so we add 2. That gives us a total of 32 valence electrons, or 16. And then we know it's highlighted here, underscored. Sulfur is the central atom. Then we have 4 oxygens bonded around it. Okay, that took care of 4. So we have 12 pair left, and we just put them around the oxygens. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then the 4 inside, 16. Okay, that checks off, we're good. And then we put the bracket with a -2. Don't forget the bracket, don't forget the charge. Okay, that designates it as an ion. Okay, it would be incorrect without the bracket or the charge. General formula, we have A, B, 4. Okay, just check that in, check that on periodic, and the shapes table, it turns out to be tetrahedral with bond angle 109.5. Okay, see, no different from the other ones, we just happen to be accounting for the charge of the polyatomic ion. Okay, cyanide. You know, this, you might recognize that because we did this one earlier. Okay. And I said, because of this negative charge, what's happened here is that hydrogen was removed. And we're going to talk about that type of chemistry when you remove it, because this hydrogen is acidic, produces, we can pull that off. And when we do that, we form this ion. So you see, initially that hydrogen brought in a lone pair of electrons. Okay, one not lone pair, but brought in 1 electron in its inventory when it was this. But then when we made it into an ion, we had to account for the negative charge, and we're going to add 1 into it. Okay, let's clear this up. And so 4 for carbon, 5 for nitrogen, and 1 for the charge, excuse me. So we got 10 pair. Okay, here, you only got 2 atoms, so there really isn't a central atom. Right? You pick any one you want there. And it's basically, you got 5 pair to work with. And so you make a triple bond like we did with HCN, okay, until everybody's fulfilled with respect to the octet. And, you know, this thing being 2 atoms is like the diatomics, they're linear. It's a linear species. There's really no bond angle to work with here because there's no bond angle. That's all I can say. Unlike hydrogen, when there was HCN, there was a bond angle. Normally that's between the central atom and whatever's bonded, whatever 2 atoms are bonded to the central atom. We don't have that here, so there's no bond angle. Okay. All right, so that is how we create the Lewis dot structures for neutral molecules and for polyatomic ions. The only difference between the two is for negative charge or positive charge, we're going to either add or subtract a number to account for those electrons that were originally there when there was neutral. All right, which brings us any questions before I proceed. Now, try some other ones, find some molecules and try them and see what you can come up with, you know. All right. Now, I've been, again, I like to introduce topics as we move along. So when we get to it, it's not so foreign. But I have been talking about how the electrons, when you got lone pair, can affect the general shape overall. And they had this model called Valence shell electron pair repulsion model, AKA Vsepr. It basically just stating what I just told you, that these electrons have an effect on the structure because electrons bonded or lone pair are charged. They have a negative charge and negatives repel. So they're going to move around to get away from each other, and that results in the particular shape, the molecular shape. Okay, and your shapes table has that shape. I talked at length about the general formula ABE. I emphasize here, this is not a real compound. It is a general equation, general formula that you obtain. You use the ABE format based on the structure you come up with. So then you can determine the geometry, okay? A is a central atom. There's always going to be 1A, and that's it. B is the outer atoms, whatever's bonded to the central atom. It doesn't make a difference what type of atom there is. It could be the same or different. And then E represents the lone pair on the central atom. I repeat, represents the lone pair on the central atom. We don't care about lone pairs sent out someplace else that are on the outer atoms, only on the central atom. When you have 2 molecules, the only shape you can get is linear. All the diatomics are linear. Okay, have no fear of ice cold beverage. Remember that? Okay, they're all linear. The one we just did, the CN negative, linear, is only 2 atoms involved there. That's the only shape that you have. The AB2 also is linear. Okay, the example we did earlier was carbon dioxide. Okay, even though there's 3 overall atoms, because of the way they're put together, you end up with a linear species. And just like diatomic, this is linear. The AB3 generally have a central atom, and then you have 3 atoms bonded to it. And the bond angle is 120, okay, all the way around. Okay, you can see here, bond angle here, 120, 120, all the way around. Okay. This is a formula for structure for formaldehyde, FYI. Okay. Formaldehyde, which is, you know, something used back in high school days when you were dissecting a pig or something. they would preserve it in formaldehyde. I don't know what they're using now because the problem with formaldehyde has been shown to cause cancer. All right, so I don't think they're using that. I don't know what they're using, but hopefully they're not using formaldehyde. Another one here is tetrahedral AB4. This is the formula for methane Ch4. It's we call this a general name. We call these hydrocarbons. Butane, propane. Notice the A-N-E. Generally, that's a good indication you're dealing with what we call hydrocarbons. And they're called hydrocarbons because the only thing associated with these are carbon and hydrogen. That's it. And this is the smallest hydrocarbon example. They can be very big. A lot of the hydrocarbons we burn could be 10, 15, even greater carbon chains. Okay. All right. But tetrahedral configuration. A special one here, this is sulfur dioxide, okay, SO2. And if you do the electron configuration, you end up with a lone pair on the central atom, which is sulfur. And its configuration is its general form is AB2E, okay? Very polar species. We're going to learn why in a bit, but that lone pair creates a polar species. Now you would think, okay, carbon dioxide would expect a similar structure. We can't because sulfur brings in an extra pair of electrons, valence electrons, and we got to put them somewhere, and they happen to go in the central atom. The point of this, totally different. Even they look the same. I mean, they look on the surface, you would anticipate them to have a similar structure, CO2 versus SO2, but totally different because of the lone pair on the central atom. Totally different properties. Then we did ammonia, has its own special name. That's the general form of AB3E, a Trigonal Pyramid. Okay, also a polar species. Bond angle, why? Less than 109, because that lone pair is forcing these hydrogens that come in closer to each other, okay, all the way around. Squished in there, you can see that. Because of the lone pair up here. Water, we did that one, AB2E2, two lone pairs in the central atom, really, really, very, very polar because of those lone pairs. Okay, so to summarize this part, okay, that if you're given any covalent compound, okay, or a polyatomic ion, be able to draw the Lewis dot structure for them, okay? Lewis dot structure, in this case, you call it electron dot structure, same thing. And from that information, determine the shape and the bond angle, which you get from the shapes table, okay? So try this at home. This, by the way, is a formula for ozone. I'll give you there's 3 oxygens bonded to it. I'll give you this part of the information right there. There's 1 oxygen is in the center, and then you got 2 oxygens bonded to that, okay? This pH3, very similar, you'll find very similar to ammonia because they both belong to phosphorus, are in the same group. Okay, so try these at home. See if you can come up with a structure. And then if you still having challenge with it, bring it back to class next Friday and we'll work it through. Okay, all right, so any questions up to this point? Because we're going to get into what's called bond polarity. Okay, no questions? This aspect, bond polarity, it's something that just keeps popping up as we go through the chapters. It has a big effect on a lot of the properties of the molecules that we work with. Okay, so we have a covalent bond, and recall what is by definition a covalent bond is the combination of two nonmetals. Okay, two nonmetals. Now, when the two nonmetals come together, when they are the same, now, to one other aspect, refresh your memory on what we talked about when we were talking about EN, electronegativity. Okay, electronegativity was the affinity of an atom that is bonded to attract onto itself the electrons, okay? And so that kind of have an effect on a chemical bond. If the affinity for, let's say, two atoms are the same, they have the same electronegativity, guess what? That bond is equal. And so the best way I can state that is, let's take the general letter A that represents a nonmetal, and the same nonmetal is bonded with it, okay? So the electronegativity of A and A is the same. So that bond that is being shared between the two is an equal sharing. There's an equal pull, okay? Now, with respect to actual bonds, the carbon-hydrogen bond is considered, and this is important, remember this, the carbon-hydrogen bond, because based on the electronegativity of carbon and hydrogen, En for both is basically the same. There's a slight difference, but negligible. So we treat the carbon-hydrogen bond as an equal sharing, and therefore, when there is no unequal sharing, it is called a nonpolar bond. Okay, what do we mean by polar? Well, things around you, we live on a polar planet, do we not? We have a North Pole and the South Pole. Okay, the battery, if you're operating a battery for your electronic device right now, that is a polar. You got a positive and a negative. Okay, so when you have a displacement between two atoms that are dissimilar, and the best way to analyze that is to say A bonded to B. B is a totally different species. That results in a polar bond because there is an unequal sharing of those electrons right here, unequal sharing, okay? Unlike the AA where there's an equal sharing. So analogous to, a tug of war between A and A, they're both 200-pound guys or women attacking that tug of war, and it's equal. Over here, maybe I got a 200-pounder versus a 400-pounder. Well, obviously the 400-pounder is going to pull a little bit harder, right? So that's unequal sharing there. Now we're going to be able to determine which one is pulling more, A or B, because if you recall from the electronegativity trend, here's a periodic table. Fluorine, which is right here roughly, is the most electronegative element, okay? And the trend was from left to right, it increased. From bottom to top, it increased. So unless we're directly dealing with fluorine, which by the way wins hands down, if fluorine is bonded to another atom, fluorine, it automatically wins, so it pulls the electrons toward it, okay? But if we're comparing, let's say, carbon and nitrogen bond, and we have to anticipate, well, in which way is the electron density being pulled? What we do is we look for the position of carbon and nitrogen relative to their position to fluorine. We can see here that fluorine is closer to, nitrogen is closer to fluorine, so its electronegativity is greater. Okay, and so in this case, the nitrogen would be the winner in that tug of war. And that's crucial because they're going to determine in which direction the pole is going. But more on that in a bit. Okay. Okay, so just a rehash, covalent bonds, you see, so we have covalent bonds and then we have a subset of these bonds. When there's equal sharing, it's a nonpolar bond, okay? When there's unequal sharing of that bond, we have a polar bond, nonpolar versus polar bond, which has an effect on the physical properties because oils are nonpolar. So if a molecule has nonpolar bonds, it could be more soluble in oils than it would in water. Okay, because polar bonds are more soluble in water than they would be in oil. Okay. Now that's not the full story because it's a general guideline. We analyze the bonds in the molecule and determine who's polar, who's not polar. If that molecule has all nonpolar bonds, then overall polarity of that compound is nonpolar. Okay, that's pretty straightforward with respect to nonpolar bonds. All nonpolar bonds, no exception, nonpolar species. But when it comes to polar bonds, we have to look at it a lot more carefully because it's related to the geometry we just been talking about. Okay, and the only way to determine whether, even though a molecule has polar bonds, they can exhibit nonpolar property overall because of the position of the polar bonds within the molecule. Okay, so electronegativity, to rehash, is the affinity for an element to attract electrons onto itself when it's bonded. When it's bonded, and not to be confused with IE, ionization energy, that one just dealt with the atoms themselves and the amount of energy to remove an electron. That's not at all related here, okay? We know that noble gases won't have an EN. Why? Because first of all, they don't form bonds, and they have their octatus will fill. So here's fluoride right there, okay? And so that's our benchmark. That's how when we do compare and contrast between two different elements, we find its relative position, relative how close they are to fluorine. And so we don't, each atom has their own electronegativity is a value that we can put on each atom. Now you can sit there and memorize all the electronegativity values for them, and that's fine. If that's what you want to do, but you don't need to because we know this is the trend. All we got to know is where it is relative to fluorine if we're doing a compare and contrast of anything other than fluorine and determine who is the most electronegative element. All right, so nonpolar covalent bonds. All of the diatomics, all of them are nonpolar bonds. Why? Because the two atoms are the same. And therefore, the electronegativity of each atom is the same, and there's no pull more than the other. They're all equal pull, okay? The carbon-hydrogen bond is also considered as nonpolar. So remember that, nonpolar for carbon-hydrogen bond. Why is that? Because the electronegativity values for carbon and hydrogen are essentially the same. Okay, negligible as far as the difference, so they're treated as the same. In polar covalent bonds, you know, one of them is holding on to the electrons or attracting the electrons more than the other. Okay, so examples of that would be like a carbon oxygen bond, a hydrogen chloride bond, sulfur fluoride bond, and silicon nitrogen bond. Notice the trend there. This is like the example of A, B, two dissimilar atoms. You're going to automatically have a polar bond. Unlike the example I said, A and A or CNH, okay? These guys are NP, non-polar. Okay? Now, this is where sometimes students have a challenge to distinguishing the two. But my suggestion is think of the AA. They're both the same. So whatever properties like electronegativity, they're going to be the same. So there's equal sharing going on in this bond here. A and B are not the same. B is not the same as A. Okay. And that means that one of them, A or B, is going to pull those electrons more onto itself, resulting in more electron density around one or the other. Which one depends on the electronegativity, of which we use the periodic table to determine which one is more electronegative, A or B. And depending on who's closer to fluorine, that gets answered, okay? And when we learn that, we can do a notation by using an arrow, which we'll show here in a bit. Okay, so this is what we mean by showing this arrow. This polarity indicates, we use symbols to indicate in which direction the pole is going, okay? Which direction is North Pole, South Pole, which is the negative, which is the positive. Now, this symbol that we have here is this lowercase delta. We have two of them, delta plus and delta negative, okay? What that means is defined as partially negative. Now recall with ionic compounds, we had a full-fledged positive and a full-fledged negative charge on these ions, okay? Like the sodium plus and the chloride negative. When they come together, they form an ionic bond, which is like two magnets come together and attaching each other. There's no sharing of electrons, okay? We call it a bond, ionic bond, but in reality, it's an attraction, electrostatic attraction, like two magnets. There's no sharing of electrons. And they have a full-fledged negative and full-fledged positive. With respect to covalent bonds, that's not the case. There's unequal sharing of that bond. And because one has a higher electronegativity, it's going to pull the electrons more so onto itself, resulting in having a higher electron density around it. And when it does that pulling, it makes the other atom have a lower electron density, therefore giving it a partial positive character and itself giving it a partial negative character. Okay, so how do we determine which direction the arrow goes? And that is determined by its electronegativity. If you look at the carbon fluoride bond, that should be a no-brainer there. Why? Because fluoride is the most electronegative element. Automatically, it's going to pull all the electrons onto itself, regardless of what it's bonded to, other than another fluoride, obviously, and then becomes nonpolar. In this case, it's bonded to carbon. So automatically it's going to have, because of the nature of the beast, the fluoride side would have a partial negative, okay, which results in the carbon side having a partial positive. Okay. Now we draw an arrow as given here, where the arrow points toward the fluoride because that is the more electronegative element or atom. And then the tail end, which has a plus symbol, is pointed toward the carbon, okay? So in this case, it's going from left to right. Now, if you look at the bond between oxygen and hydrogen, no question asked, oxygen is a lot more electronegative, because if you look at the periodic table behind me, hydrogen's in the far left, oxygen's way over in the far right. And so the arrow goes from right to left. Oxygen is on the partial negative is on the oxygen, partial positive on the hydrogen. That's, if it was written the other direction in this manner, and it can be, we just reverse the arrow. That's all, no big deal. Reverse the arrow and put the partial negative over here, partial positive over here. This electronegativity is crucial, especially from an organic chemist standpoint. Because when I said earlier, we're looking at the structure of the compound, we're looking for areas that we can tap into to change the structure. And we can really only do it fairly readily where there are polar properties in that molecule. And things like this, where we have the similar polarity, allows us to change that area. So polarity is, and electronegativity is very crucial. Now we look at the bond between the phosphorus and the chloride. Okay, chloride is the most electronegative between the two based on its position on the periodic table relative to fluorine. And so the partial negative goes on the chloride, partial positive on the phosphorus, and the arrow goes from right to left to right, excuse me. Again, I emphasize this. If it's reversed as far as displayed, just reverse the arrow in another direction. That's it. Okay. Okay. Partial charges. So obviously with noble gases again, noble gases, because of their nature, they will not bond or anything of the sort. You may be given examples like we just talked about. You may be given a carbon-oxygen bond and being asked to add the delta notation, okay, which is the partial positive and negative, and then the polarity arrow. And to answer that, you got to figure out who's the most electronegative, and that determines that. We know that oxygen is a lot more electronegative than carbon, so the arrow here goes from left to right. We put a partial negative on the oxygen. Nitrogen fluoride, no questions asked. Fluoride is the most electronegative, so the arrow goes to the fluoride. Also, the partial negative goes to fluoride. Here, we did this before. Oxygen is more electronegative, so the arrow goes from right to left. And in this case, the chlorides are a lot more electronegative than carbon, so the arrow goes from right to left. Partial negative on the chloride. Carbon hydrogen, none. Why? Because carbon hydrogen bond, as we stated, the electronegativity value of each one is essentially the same, and therefore negligible, and therefore we treat it like the diatomics. We have no dipole. Okay. And so all of these on the left will exhibit polar character. Okay. Because of the polar bond there, polar character. And the one thing about these arrows that the polarity arrows I need to explain is this, because it's going to help us to determine why these things, when we put them in their configuration, why they cancel out. These arrows are nothing more. We use this a lot in physics. We're using a lot of things. It's called a vector. We're not going to get into vectors and so forth, okay? But basically, a vector is a quantity that has both magnitude and direction. For example, magnitude, I could say 20 miles. Okay, it doesn't have much information given to you. It's 20 miles, that's it. But if I say north 20 miles, now you got direction and magnitude. That arrow has magnitude and direction. So the way they are written in this manner right now, given the shape, the size, the arrow could represent a magnitude. And right now, the arrows are all the same quantity. In reality, some can be shorter than others, okay? Or it could be, something like this. But this one here, on the first one, this is going in the positive direction, okay? Also, this is positive, but this one is going in the negative direction. It's going from right to left. Also, this one is also negative direction, okay? So that's that arrow, the last two are going in negative direction. What that means is that if I have two arrows, two vectors going in the same direction, okay, and for whatever reason, maybe each one is 10 units, then the total units here is 20 units, okay? Between these two vectors. But if one vector is reversed, same magnitude, and is going the opposite direction than the other one, okay, the one on the right is going in the positive direction, while the one on the left now is going in the negative direction, so that's -10. The net sum is equal to 0, okay? And so the arrows cancel each other out because they're going in the opposite direction, okay? So what that means, you extrapolate that information and we go into the structure. And if you identify the polar bonds, and if the polar bonds if the polar bonds go in opposite direction from each other, guess what? They cancel each other out. And when polar bonds cancel each other out, the net result is that molecule is nonpolar. If the polar bonds do not cancel each other out, the net result is the molecule is polar. See how that works? All right, so you can have a molecule that has polar bonds just by virtue of the two atoms we're looking at are dissimilar. But because there's another one in the molecule going in opposite direction, the overall net polarity is 0, resulting in a nonpolar species, okay? I'll give you some examples of that in a minute. All right, here you make your answer. Are these bonds ionic, polar covalent, or nonpolar covalent? Well, to answer the first part, ionic bonds is a combination of a metal and a nonmetal, okay? And the only one here that I see is ionic is the sodium chloride. All the other ones are covalent. But, so this one's ionic, no questions asked, sodium and chloride. Everyone else is covalent. However, if you look at the Br, bromine, they're both the same, right? Both the same atoms. So we have a nonpolar species here. Everybody else that's left over, yes, it's a covalent bond, but two different elements, nonmetals. Automatically, we have a polar compound. A polar bond, I should say, not compound, polar bond. Polar compound depends on the overall geometry. We'll get that here in a second. Okay, so we got nonpolar, polar, ionic, and polar. All right, so polarity, very important chemistry concept, and it comes up later over and over and over again, okay? Just think of it as a tug of war of electrons, bonded electrons, okay? And it had nothing to do with lone pair, bonded electrons. All right, so if we look at this, again, very similar, they want to know, identify as ionic, polar, or nonpolar. Well, sodium chloride, we know that. It's metal, nonmetal. It is ionic compound. Has nothing to do with polar bonds or nonpolar bonds. It's a separate thing, separate class in itself, just ionic bonds. That's all you can say about it. HCl, it is a covalent bond, but two dissimilar atoms, right? Hydrogen and chloride. So automatically polar covalent. Okay, two dissimilar. In fact, HCl is what's in your stomach right now. That's otherwise when it's an aqueous. Quick thing about naming, which, by the way, nomenclature exam. Some of you haven't attempted it yet. I would suggest that you have unlimited attempts. The score, the highest score is capped. You got to score an 80% to keep that. It will keep anything greater than 80%. But HCl, when it's in water, it's called hydrochloric acid. But if it's out of water, like a gas, it's called hydrogen chloride. So if they classify it as an aqueous, it's called hydrochloric acid. If it's not aqueous, then it's hydrogen chloride. So either way, this is a polar covalent bond. Next one, we got two hydrogens, two of the same atoms, equal tug of war, okay? Non-polar covalent. Chloride, carbon, automatically two dissimilar atoms, you have a polar covalent. Carbon, hydrogen, we talked about that. The electronegativity is the same, so we have a non-polar covalent bond. Oxygen, oxygen, it is a diatomic. through the two similar atoms, just like hydrogen. And so we have a nonpolar covalent. Potassium and oxygen, we have a metal and a non-metal. Okay, so it is straightforward ionic, nothing to do with being a polar bond or a non-polar bond. It is in itself polar because it will dissolve in water very readily. Okay, but we're just talking about the fact that it's a metal and a non-metal. It's simply an ionic compound. Then phosphorus and fluoride, to the similars, no question here, polar covalent bond. Okay. All right, so once we identify the molecule, so what we do first is we're given the formula. From the formula, we go to the Lewis dot structure, count up the valence electrons, come up with a geometry, okay, and a three-dimensional model of what we're looking at. And then we look at each individual bond and determine whether we got any polar bonds in there. Once it were nonpolar, if it's all nonpolar bonds like carbon, hydrogen, then it's a nonpolar molecule overall, okay? If we have polar bonds and they don't cancel each other out, then we have a polar molecule. If we have polar bonds and they cancel each other out, then we have a nonpolar species. I got tongue-tied there for a second. So all nonpolar bonds, nonpolar molecule. Remember that example we did earlier with SO3, SO2, we had a lone pair in the central atom. Because of that lone pair, it causes this bond angle to decrease. We could draw this and we think, okay, we got sulfur in the middle, a single bond there, double bond there. And we say, oh yeah, we got a polar bond in that way, polar bond in this way. Okay, you would think, all right, that polar bond cancels out the left and the right, but it doesn't. Why? Because that lone pair causes that angle to be smaller than 120. And look what happens to that polar bond. This one goes to the southeast direction, and this one goes to the southwest direction. And so they don't cancel each other out. And so the result is it has a polar molecule because the polar bonds do not cancel each other out. See how that works? Now, if we look at carbon dioxide has polar bonds. One going from left to right between the carbon and hydrogen, and the other one going from right to left. Carbon, hydrogen, because they go in exact opposite direction, they cancel each other out. The polar bonds cancel each other out, resulting in a nonpolar molecule. Okay, polar bonds don't cancel out, we got a polar molecule. Polar bonds do cancel out, we have a nonpolar molecule, even though there are polar bonds within the molecule. Now, another configuration that bonds cancel out is the tetrahedral. You might find it a little bit challenging to see that, but I don't have, let's say we got a carbon that has 4 bonded fluorides. So I'm trying to draw it, kind of give you a perspective. This is my attempt to give you a 3D perspective in a 2D world. Okay, and so better yet, let me do this. All right, so we have carbon, and then we say it could be chloride. Let's put chloride. All right. Now this wedge kind of represent that bond coming out of the screen, and then this hash mark kind of represents that bond going back into the screen, kind of give you a 3-dimensional model. Okay, we can see here that we have 4 polar bonds, and they're all going toward the chlorides because chlorides are more electronegative. Okay, Now, what's more difficult to see is that these four polar bonds, because of the geometry, I mentioned earlier that these arrows represent vectors, and these vectors are made up of what are called scalars. That's not important, but if you break it down, the result is mathematically these four bonds in the tetrahedral, the AB4 tetrahedral configuration, end up, you got four polar bonds, but because of the geometry, we end up with a non-polar molecule. Okay, because all these four bonds with respect to the polarity cancel out. Okay, now, if I were to take one of those chlorides and replace it with, I don't know, hydrogen. Okay, what happens there is now three polar bonds and one nonpolar. The moment I stuck in one nonpolar, this is a nonpolar bond, I end up with a polar molecule. In fact, if I do that all the way around, I still have a polar molecule. I go up to the third one, still have what am I saying? Polar molecule, okay? But then I go back all the way around the horn, and now I put all four of them back to hydrogen. Guess what? I go back to nonpolar. Okay, because of the geometry and the fact that I got just hydrogens here, all four hydrogens makes it nonpolar. But if I put anything else in there, in placing that hydrogen, go all the way around to replace the third one, I still remain as polar, but the moment I replace the last one, it goes back to nonpolar. Okay. So the geometry is very crucial in determining the overall polarity of the molecule. Okay. All right. So, methane, we talked about this, which is CH4. It is all nonpolar bonds, carbon hydrogens. So the fact that they're all nonpolar bonds, regardless of the geometry, it is a nonpolar molecule. PCl3, we have three polar bonds. In fact, if you were to draw the Lewis dot structure, you will end up with this. And guess what? You end up with a lone pair on the central atom. Okay. The fact that you get a lone pair that shows this bond angle, which we would anticipate to be 109.5, but because there are lone pairs in here, that shows this, we got less than 109.5. And these three polar bonds do not cancel out. Therefore, we end up with a polar molecule overall. Okay. And then we talked about carbon dioxide, the fact that the polar bonds cancel each other out because they're going in different direction. We have a nonpolar species. All right, so we talked about ammonia, we talked about water, so we don't have to go at length. So you can practice again, be able to answer these questions whether the molecule is polar or not. Okay. All right, with that in mind, congratulations, you have completed chapter 7. Tell you what, let's take a quick short break. And then let's say I got 1:34. Let's come back in about 15 minutes and we'll start on chapter 8. Okay, any questions before I continue? No? All right, then I got 1:34. Let's come back at 1:45. Okay. Okay. I'm back. Any questions? On the course, I put a simulation that kind of You may want to take a look at it. It's under additional resources in that module, additional resources that has to do with polarity. It's a simulation. You may want to go in there and play with the simulation to give you help you get a perspective on polarity. Okay. All right. Any questions? Well, if not, let us continue with chapter 8. Chapter 8 deals with nomenclature. Now remember, there is a separate exam on nomenclature, and you have a multiple of attempts, so don't hesitate to go in there and do it as many times as you need to get the 80%. Now, I'll answer a question I've been asked. What do I have to take it? Well, like anything, you can take it and end up with a 0 and accept the 0, but keep in mind it's 10% of your grade. So if you're at the borderline, it could push you up to the next grade, and the same token, it can push you down. Okay, so keep that in mind. Now, right now, also another thing to keep in mind is that Canvas doesn't give you, it just grades you. You have your grade based on what's been graded and what's been done. So it doesn't take into account any future assignments. So right now, there are no grades in the nomenclature. Now, what's going to happen in about maybe 2-3 weeks, I'm going to go in there and put a 0 in there. Okay, now why do I do that? I do that for a reason, because it was something learned way back in the beginning. Was this because without that 0 and you don't take that exam, it gives you a false image of what your grade is, because like I said, Canvas doesn't take into account that particular assignment. Now, when I put the 0 in there, if you're not taking an exam, your grade will drastically drop, and it kind of alerts you as to, oh, okay, now I know where I'm at, truly know where I'm at, because now I throw in the 0 for the nomenclature exam. Okay, so, and then that way it gives you a heads up that, okay, it's an assignment I got to do. Keep that in mind, and I go ahead and try to knock it out. All right, so enough on that. Nomenclature, basically name that compound. You also have a guide or tool in the course website that aids you. It's called StudyMate, that will aid you with nomenclature. So you're not used to it, it's basically, given this formula, give the name and vice versa. Okay, so use that to help you out. But naming the atoms are pretty straightforward. If they're the neutral atoms, they have their own name. We just follow that with the word atom. So when we're talking about sodium, it's called sodium atom, neon atom, etc. Okay. Now, be familiar with the first 20, and then on top of that, we're going to have barium, which is Ba, cobalt, iodine, copper, C is copper, Fe is iron, Pb is lead. We have Hg, which is mercury, which is sometimes confused with Ag, which is silver, which is also confused with Au, which is gold. Okay, so we got mercury, silver, and gold. Then we got zinc, and then stannous. This can be one or two names, stannous or tin. If you look at your toothpaste container and look at the ingredients, you may be brushing your teeth with stannous fluoride or sodium fluoride, but a lot of it's stannous fluoride. You're brushing your teeth with the ion of tin. Then you got strontium, nickel, bromine, chromine, manganese, and cadmium. Okay. So be familiar with those the first 20, and then we will. Let me call up the first 20. Okay, so on the far left, obviously we have hydrogen right here, then it jumps over to helium. Then we got lithium, a beryllium, boron, carbon, nitrogen, oxygen, fluorine. Notice I said fluorine, that's the element. Fluoride is the ion. We got Ne for neon. We got sodium here on period 3, and then followed by magnesium, shoot across to Al, good old L for aluminum, Si for silicon, P for phosphorus, S for sulfur, Cl for chlorine, Ar for argon, followed by K for potassium, and then number 20, Ca for calcium. Okay. All right. Now, for ionic compounds, the naming is basically name of the metal, and then we add the name of the nonmetal. Okay. But the nonmetal name has been changed from the atom to the ion. Okay. And the best way to do that is to come over here, and we have nitrogen, which becomes nitride, oxygen becomes oxide, fluorine becomes fluoride, phosphorus becomes phosphide, sulfur becomes sulfide. Notice the trend here, right? Cl becomes chloride, and Br bromide and iodide. Okay, the other ones that come into play, but those are the ones I've circled, the major ones you see more often. Okay, so the IDE tells you that you are dealing solely with the single element. So fluoride is the single element fluoride. Notice what happens here with the sulfur, sulfide. Now, by itself, just sulfur is called sulfide. But if we combine it with oxygen, for example, what I've written here in the polyatomic ions, you have sulfate, ATE, where you have sulfur bonded with 4 oxygens, and then it has a -2 charge. And then sulfur with 3 oxygens have a -2 called sulfite. Okay. Now, I also have in the nomenclature module some additional information that we're going to go over this that are given with respect to, we call these polyoxy ions, sulfate, sulfite. Notice with nitrogen, the same scenario. You start off with nitrogen, the element, it becomes an ion, which is nitride. And then when you add oxygen, 3 of them specifically, it becomes nitrate. 2 of them becomes nitrite. Okay, so you have the nitrogen, you had the IDE, nitride, and then you got the 8 and the ite. And that the 4 different items, and be able to distinguish them, because sometimes you're given the formula and you got to give the name, and sometimes you got the name and you got to convert the name into a formula. Okay. Another aspect about this is the following. I have circled in red the ions that 100% of the time their particular charge. Okay, everybody in group 1 right here will always, when they become ionic, will always have a +1. So there's 6 of them. There's 6 elements that their charge when they become ionic. Everybody in group 2A will always have a +2 when they lose those 2 electrons. Okay, so now you got 12 elements that 100% of the time. This is important. 100% of the time, their oxygen. They don't have any different charges on it. That's always their charge. Then we're going to add 4 to the list. Aluminum here, Al, number 13, always has a +3 charge, 100% of the time. Zinc always has a +2 charge. And silver always has a +1 charge. okay? Then followed by cadmium that has a +2 charge. Excuse me, silver has a +1, okay? So guess what? You have 6 here, 6s12, 13, 14, 15, 16. You have 16 elements that when they become ions, you know 100% of the time their particular charge. What that means that everybody else varies in oxidate and charge. It's variable. For example, copper, you have 2 types. You can lose two electrons and you end up with a copper +2. You can lose 1 and you end up with a copper +1. Okay, it's unpredictable. But those 16, I call them the sweet 16, you know 100% of the time. For these guys here, the nitrogen and the phosphorus, when they become ionic, -3. Oxygen, sulfur, -2. All the halides, -1, 100% of the time with respect to their charge. Okay. All right. Give me 1 second. Somebody's at the door. Sorry about that. It's a bad thing about teaching at home. Doorbell rings. You can answer it. Okay, so those 16, you always know the charge. Okay, why is that important? We're going to learn that because when we start putting these molecules together, sometimes you don't know what the charge is on the partner, but you always will know the charge of the other species. And knowing that when I put these together, I always have to add enough of the positives and enough of the negatives. So when I put them together, they end up with a 0 charge. So we can calculate what the charge is for the other partners. And we may need to know that to give it the name. Because the ones in circle, like for example, if I have sodium and chloride together, it's simply sodium chloride. But if I use copper and chloride together, I have to be specific because copper can exist as either copper 2 or as copper 1 is shown there, okay? And so I have to use Roman numerals in parentheses to distinguish between the 2 coppers. So I would have to say copper Roman numeral 2 or copper Roman numeral 1. And which one I use would depend on how many chlorides I have, because I know that the chlorides always have a -1. And if I have two chlorides, then that means that I have copper 2. So we'll get some examples of that here in a bit, okay? All right, let's go back to the compound. Okay, so as a refresher, covalent compounds are nonmetals only. Now, the thing about nomenclature when it comes to ionic compounds and covalent compounds, put this in long-term memory. With ionic compounds, we don't use prefixes, okay? Like, for example, let's say we're dealing with calcium chloride. This should simply be calcium chloride, okay? Its particular name. And we'll explain why there's 2 of them. But notice with a covalent compound here, this is carbon dioxide. The prefix di designate is 2. So for covalent compounds, we do use prefixes, okay? Not so for ionic. So this would not be calcium dichloride. That would be incorrect in nomenclature. That is not the rules for nomenclature. Now, these rules are worldwide rules. There's an organization called, the letters IUPAC, but that's not important. Everyone around the world has agreed that this is the way you're going to name this particular compound. Everybody agrees on that because at one time, with so many compounds out there, there's a lot of ambiguity. And so we're trying to eliminate that ambiguity. So everybody in the world names these compounds the same way. So the takeaway here, ionic compounds, no prefixes. Covalent compounds, yes, prefixes, okay? We'll get some examples in a bit here. Okay. Monoatomic ions, things like sodium, chloride, and potassium. The polyatomic ions that I discussed these from the periodic table, bottom left, they have their own specific name. We don't change them, like the nitrates, the nitrites, the hydroxides, so on and so forth, the ammonium, okay? That name stays whatever it is, and that formula stays whatever it is. That would not be called phosphorus oxide. It's phosphate. That's it. The OH next to it would be called hydroxide, and the carbonate, etc. Okay, so it wouldn't be carbon trioxide. It's not even, no, because these are ions and they have their own specific name and charge. Okay. Up to this point, I've been using the term their charge, the charge of the ion. Sodium had a +1, the sodium ion has a +1. I'm going to start from this point forward. And I fall back once in a while, but start using the word oxidation state or the oxidation number, because when we talk about ionic compounds, there's no question, there's a specific charge, a +1, +2, -1, -2, -3, no question about that, right? Full charge. But covalent compounds, remember the delta notation, it's a partial charge. So it really doesn't have a charge. It's just a partial charge. And so, and there's a little bit of ambiguity there. So what we do, we use the term oxidation number. So the oxidation number for all elements are 0, obviously, because we have an equal number of protons and electrons is 0. Okay, and they have, depending if it's a metal or non-metal, their oxidation number will change. So group 1 will have an oxidation number of +1. Okay, group 2 will have an oxidation number of +2. There are 16 elements that I showed you already that have a fixed charge. And those guys that I highlighted in red, having a fixed charge, we don't use a Roman numeral. Unlike the copper example I talked about, where we used a Roman numeral to distinguish the two, okay? All right, so they have variable charge, these other ones. So we know that metals lose electrons to become cations. So we know that group 1A has a +1 oxidation number, +2 for group 2A, +3 for group 3A. Cadmium and zinc always have a +2, silver always a 1. Rehash of what we talked about. What that tells you, all the other ones, other than the sweet 16, their oxidation number can vary from a +1 to a +9. It all depends on the reaction conditions and what's going on. Okay, so it does vary. So what we do is to distinguish the variable oxidation number of these metals, we use Roman numerals. For example, copper +2, we would write as copper parentheses, Roman numeral 2 and parentheses. Now, some people, I don't know, I guess they don't teach this anymore, but Roman numerals, that's the way they used to count a long time ago. I is 1, we use capital, not the lowercase. I is 1, 2, like this is 2. So we got 1, 2, 3 I's is 3. Now we put an I in the V, that's 4. We put the V, that's 5. V plus 1 is 6. V plus 2 I's is 7. V plus 3 I's is 8. And then we have 9 is I and X. I first, that is 9. And then we got X, which is 10. Okay. So the I in front of the X means subtract 1. If it's after the X, you add 1. Okay. And it's interesting about these Roman numerals because they don't have a 0. I don't know how they did their mathematics without a 0. So who knows? Concept of 0 was not there. All right, so we use Roman numerals, uppercase Roman numerals to distinguish the other variable metals with variable oxidation states, okay? I've been asked the question, well, do we put a space after the word and then does make a difference? I'm going to talk about right here, okay? If you write it with no space or with the space, I should say, and Canvas gets it wrong, counts you wrong, let me know. I will correct that for you. We're trying to train Canvas to understand the space, and obviously we haven't caught all of them. So I will give you credit for that, obviously. Okay, the point takeaway here is this: those 16 elements that you know the oxidation state 100% of the time, no Roman numerals. Everybody else, Roman numerals, okay? Non-metals, obviously they gain electrons. Group 5 have a -3, group 6, -2 oxidation number, and 7 has -1. Obviously noble gases have a 0, okay? Ionic compounds, metal and non-metal combination. We begin by learning the formulas for names. Remember that ionic compounds are made up of ions, and ions have a charge. Okay. Now, the general formula to remember is, I can write it this way: the number of cations plus the number of anions, when you put these together, should equal 0, okay? So you got to add enough cations and enough anions to equal 0. And that equation will do very well for like 99% of what you're doing. Occasionally, you have a polyatomic ion and you need to calculate the oxidation number of maybe the central atom. And that polyatomic ion has a charge. So maybe what's best is to say instead of 0, it should say the oxidation number of the ion or compound, okay? And I'll do some examples of that to demonstrate the general equation. Okay, the sum of the charges must equal 0. We found, I talked at length about these polyatomic ions, and this is by no means a full list of all of them out there, just the ones that we're going to work with, okay? And we keep these together. If for some reason we need to add more than one, let's say nitrate, if for some reason we're going to add one more, maybe 2 or more of nitrates, guess what? We use parentheses where X represents whatever number we need. If we only need 1, no parentheses, but if we need more than 1, we put that whole unit, the NO3, and that goes for all of these polyatomic ions. We put them in parentheses, and then we do a subscript to designate how many of these polyatomic ions we need, okay? All right, so compound must be neutral. We got to add enough cations and ions to equal 0. So sodium, the oxidation number of the ion for sodium is a +1. The nitride is a -3. So what I do is I just put them together here, and I know that I got a -3. Now, I need to put enough of each so they cancel out. That doesn't make sense that I need 3 sodium ions to cancel out the -3 of the nitrides. Yes, so that 3 that I put up there in front of it becomes the subscript for the sodium when I write the name, the formula. So there are 3 sodiums because each one has a +1 for every nitride because the nitride has a -3. Okay. So this is the formula. And the name is simply sodium nitride. Okay. And so I'm either going to be given the formula and be asked to name it, or I'm given the name and I'm asked to give the formula. So I have to decipher the name. That's why it's important that we understand the IDE and the ATE and the ITE. Okay, the nitride, the nitrate, then nitrite. Okay, whenever you hear the ate and the ite, go to the polyatomic ion. When it's the IDE, IDE, is just the single atom itself. Okay, so here's the formula. Let's try sodium and sulfur. Well, we convert the elements into the ions. And again, we know from the example we just did that sodium has a +1. It's in group 1, has an oxidation number of +1. The sulfur is in group 6, and it's a nonmetal. So its oxidation number as a ion is a -2, okay? And so we convert them into ions, that's first. And then from that, we know how many of each we need to add to put them together. So this tells me I need 2 sodium ions for every sulfide. So the formula becomes Na2S. All right, now we have magnesium and oxygen. Convert them into the ions. Magnesium is a group 2. So its oxidation number is a +2. It's a metal, it'll be a +2, right? Oxygen, like sulfur, is in group 6. So it becomes an ion with a -2. Now I put them together, and guess what? I got a +2 and a -2. I can put them together as a 1-to-1 ratio. So it's just simply Mg. So the name is magnesium oxide. Up here was sodium sulfide. So sodium sulfide, this one becomes magnesium oxide. Okay, I'll get the names on these here in a bit. Potassium. Potassium is a group 1 metal, ends up with a +1. Okay. Phosphorus is in group 5, has a -3. So then I need 3 potassium ions. And so its formula is K, because I need 3, subscript 3, P, potassium phosphate. Okay, this is a little more challenging. Okay, let's work this through stepwise. Okay, calcium, break it down into the elements first. We have calcium +2. It's a group 2 element. Okay. Nitrogen's group 5A, so it has an oxidation number of a -3. Now think about this for a moment. I'm trying to put together a +2 and a -3. Unlike the previous 3 examples, it was pretty straightforward. I need 3 of these, 2 of these, whatever the case may be. Over here is not so much, right? So I got to put them together so the overall charge is neutralized. So how do I do this? Well, think about this for a second. If I were to, let's think about fractions for a minute. Let's say we got 1/4 plus 1/3. I can't add those 2 fractions together as written, right? What is it that I need to add together 1/4 plus 1/3 to get an actual value? Anybody know? What do I need to do to this so I can add it? Because I can't add it like that.
You have to make the denominators the same.
Yeah, I need to find the lowest common denominator, remember? And one way is maybe I can multiply the two denominators, and it looks like maybe 12 is the lowest common denominator, okay? And so I convert the fourth to 12s and the third to 12s, okay? So that being the case, look at here. I can do a very similar thing with the 2 plus 2 and the 3. What number is common with them? Isn't it 6, right? And so if I get 3 plus 2s, doesn't that give me a total of plus 6? And if I get 2 plus negative 3s, isn't that a total of negative 6? And when I put these together, oh, look, plus 6, negative 6, they cancel each other out. So I need 3 calciums and 2 nitrites. So that 3 becomes the subscript for the calcium, and that 2 becomes the subscript for the nitrite, okay? So I need 2 nitrites because each one has a negative 3, which gives me a total of negative 6. And I need 3 calcium ions because I got a plus 2, and that's a total plus 6. So my common factor is a 6. So I can, that tells me how many of each ions I need. So the formula in that case becomes C, calcium subscript 3, nitrite subscript 2. Okay. Now, aluminum is one of the sweet 16, always has a plus 3. Okay. The chlorides is in group 7, becomes an ion, has an oxidation number of a -1. So that means I need 3 chlorides for every aluminum ion. So our formula becomes Al subscript 3. Okay, zinc has a plus 2. Okay, iodide has a -1. So I need 2 iodides for every zinc. So my formula becomes ZnI2. Okay, now we get the Roman numerals, okay? That Roman numeral pertains to the copper. And what it's telling you is the oxidation number of the copper. So this is a +2 ion. The oxygen becomes oxide with a -2. Here we can simply put them together 1 to 1 because I got a +2 and a -2. So it's a simple CuO ratio, 1 to 1 ratio. Okay. And we're going to get to the names here in a bit. And then here we got lead. Lead is, there's telling you, again, this is telling you that is a +4. So it's Pb +4. And the oxygen becomes oxide, is a -2. And I got to add enough oxides to cancel out the +2. So I need 2 oxides for every +4 lead. Okay. So its formula becomes as follows: PbO2. Now, let's work on the names now. From 1 through 6, all of them, all the metals were part of the sweet 16. Therefore, they did not require Roman numerals. Therefore, their name is straightforward. Sodium sulfide for the first one. Magnesium oxide. Potassium phosphide. Calcium, calcium, I guess I don't know how to spell here, calcium nitride. Okay, notice and no Roman numerals, right? And then aluminum chloride, and then zinc chloride. Chloride. That's for the first six. So hopefully you can read my writing there. I'm kind of writing pretty quick. Okay. Now we come to the variable oxidation numbers, and we have to incorporate the Roman numerals when we name them. Okay, so Cu is copper, and we maintain the Roman numerals that we were given, and then oxide. So this is copper 2 oxide compared to copper 1 oxide. It's, it's a totally different element. It has one oxidation state for that copper. And then the last one would be lead, Roman numeral 4. Okay, so don't forget the Roman numerals oxide for the variable oxidation number elements or metals. Okay, now you can mix and match. Notice I did sodium sulfide, but guess what? You can go sodium oxide, sodium phosphide, sodium nitride, sodium chloride, sodium iodide, and guess what? Sodium oxide. You could do the same thing with magnesium over and over, so you can mix and match. Already you should have a couple, 400 or 500, 400 or 500 compounds, mixtures that you can mix and match already. Okay, we did copper 2, but you can do copper 1 oxide, copper 1 chloride, so on and so forth. See how you build up your database? Okay. All right. I'm going to stop it here. Okay. Okay, so slide number 10. Let's stop it here. And we'll continue with slide number 10 next Friday.